Question number 1. A uniform solid cylinder of mass m, radius r is set in rotation about its axis with angular velocity omega naught. Then lowered with its lateral surface on the horizontal plane and released. The coefficient of friction between cylinder and plane is given as mu, the time after which the cylinder starts rolling without slipping. So, initially the cylinder is under rotation with angular velocity omega naught. So, after some time interval, according to given data here, cylinder starts pure rolling, indirectly cylinder starts rolling without slipping. So, in this case it begins to roll with slipping after some time interval, here it starts pure rolling. At that time its velocity v equal to r omega. Now, I am going to find this value of v and also omega after t seconds. So, while it rolls, it tries to slip. So, due to that frictional force will be in forward direction. So, due to this frictional force it attains with a linear acceleration a. So, due to this frictional force which is equal to limiting friction, this is the reason for the linear acceleration of the cylinder, that equal to ma. In place of frictional force, that is I write mu mg is equal to ma. So, with what linear acceleration this cylinder attains during this rolling with slipping until it attains here v equal to r omega. So, in this case a is equal to, here it is, mu g is the equation for acceleration of the cylinder which rolls from impure rolling to pure rolling in this time interval. So, now I am going to write the equation for velocity of this cylinder after t seconds. V equal to initial velocity u plus at. So, u plus at, initially it starts from rest according to given data, starts from rest, it is just released. So, due to that its initial velocity is 0. So, v equal to, in place of a I write mu g. So, mu gt is the velocity of the cylinder after t seconds. You take it as equation 1, you take here it as equation 2. Now, once body is under rolling, immediately you have to consider force equation and torque equation. So, force equation is over, F equal to mu mg. Here cylinder attains positive acceleration until it attains pure rolling. At the same time, here this frictional force acts opposite to the direction of the rotation of the cylinder. So, due to that cylinder attains negative angular acceleration. So, for this here it attains negative angular acceleration. So, therefore, I write the equation for torque on the cylinder. This torque against this frictional force is equal to F into R. So, torque is equal to I alpha, that equal to, in place of F I write mu mg into R. But for cylinder moment of inertia is mr square by 2 into alpha equal to minus mu mg into R. So, from this we get alpha equal to gets cancelled, R gets cancelled, minus 2 mu g by R. Minus 2 mu g by R is the angular acceleration of the cylinder in between impure rolling to pure rolling. Now, what is the angular velocity after t seconds? After t seconds, angular velocity of the cylinder is omega naught plus alpha t. So, omega naught instead of alpha I write minus 2 mu g by R into t. So, okay, here in this case omega, what we want here? So, you multiplied with R on both sides, then we get R omega is equal to R omega naught minus 2 mu gt, but this R omega is V equal to R omega naught minus 2 mu g into t. Already we calculated the linear velocity of the cylinder after t seconds. Linear velocity of the cylinder after t seconds is equal to, here it is, mu g into t equal to R omega naught minus 2 mu gt. So, this mu gt is taken towards left side, we get 3 mu gt is equal to R omega naught. So, from this the time after which cylinder attains pure rolling is t equal to R omega naught by 3 mu g is the answer for time after which cylinder attains pure rolling. Once again, here when cylinder is initially under rotation with angular velocity omega naught, and it is just laterally placed on horizontal rough surface, then it tries to slip towards left side. So due to that, frictional force will be in forward direction. It leads the acceleration of the, it leads the linear acceleration of the cylinder. That linear acceleration is due to frictional force. So due to that, I write limiting frictional force as mu mg on horizontal surface, that equal to ma. From this, I calculated linear acceleration of the cylinder as mu g. So just after attaining pure rolling, let its velocity of center of mass is v. Indirectly VCM. That velocity of center of mass is VCM, that equal to v. So v equal to u plus at, but initially it starts from rest. So therefore, velocity of center of mass just after obtaining pure rolling is v equal to mu g into t. So this is the velocity of the cylinder after attaining pure rolling. Now here in this case, what is the torque acts on the cylinder at that time? So frictional force acts in forward direction. Cylinder has to roll like this. So due to that, the torque due to this frictional force opposes its rotation. For that reason, it attains angular acceleration. Therefore, torque is equal to I alpha is equal to minus of mu mg into r. So r gets cancelled. From that, alpha equal to minus 2 mu g by r. So after t seconds, angular velocity of the cylinder just after attaining pure rolling, omega equal to omega naught plus alpha t, omega naught plus, instead of alpha we write minus 2 mu g by r into t. So from this, omega equal to omega naught minus 2 mu g by r into t. You multiply with r on both sides, we get r omega equal to r omega naught minus 2 mu g into t. But after attaining pure rolling, the velocity of the cylinder, nothing but indirectly, the velocity of center of mass of the cylinder is r omega. So I have written r omega as v equal to r omega naught minus 2 mu g t. But after t seconds, what is the velocity of the cylinder? That is mu g into t equal to r omega naught minus 2 mu g t. So this mu g t is taken towards left side. We get 3 mu g t equal to r omega naught. From this, t equal to r omega naught by 3 mu g. So after what time interval this cylinder attains pure rolling, that is r omega naught by 3 mu g, is the answer for question number 1. So answer is r omega naught by 3 mu g. Answer is C for question number 1. It is one of the standard model question regarding impure and pure rolling of a body on horizontal rough surface. So this frictional force sometimes helps for rotation. Here in this case, frictional force, the torque due to this frictional force opposes the angular velocity or angular rotating cylinder until it attains pure rolling. So due to that, here it attains angular retardation. For that reason, I considered alpha as negative. So after t seconds, angular velocity of the cylinder as omega equal to omega naught minus alpha t. In place of alpha, it is replaced by 2 mu g by r. So after that, we calculated the equation for the time after which the cylinder attains pure rolling as r omega naught by 3 mu g is the answer for question number 1. So what is the one of the standard model question? So I have to keep this point in mind. Next question. A wheel is rotating about an axis through its center at 720 revolutions per minute. It is acted on by constant torque opposing its motion for 8 seconds till it comes to rest. The number of revolutions made by the wheel in 8 seconds is, the wheel is rotating about an axis through its center. This is the wheel. Rotating about an axis through its center is 720 revolutions per minute. So 720 by 60, 720 revolutions by 60, that is per second. So 720 by 60 is the number of revolutions per second. Indirectly, it represents frequency of rotation of this wheel. Okay. Now it is acted upon by constant torque opposing to its direction. Suppose it rotates like this, so constant torque is applied opposite to the direction of the wheel until it comes to rest. So final angular velocity becomes 0. Initial angular velocity is given as 720 revolution per minute in terms of frequency. Okay, now in this case, what is the average angular velocity of this one? Average angular velocity is, because you are applying constant torque acts on the rotating wheel. So average value is simply initial plus final by 2. If it is not constant torque, then that formula is not applicable. So here constant torque is applied on the rotating wheel but in opposite direction. So the angular velocity of the rotating wheel is average of these two values. So 0 plus omega naught by 2. So due to this average angular velocity, this wheel supposed to make an angular displacement theta in t seconds, that equal to omega naught by 2. So from this theta is equal to omega naught into t by 2 is the equation for angular displacement after t seconds. But we want here it is, we want angular number of rotations, number of revolutions made by the wheel within 8 seconds. So by dividing with the 2 pi on both sides, we get omega naught. Omega naught can be written as here 2 pi into mu naught. So mu naught into t by 2. So 2 pi into mu naught is the initial angular velocity. So this 2 pi is taken under theta. So this is the number of revolutions made by the wheel in 8 seconds. So mu naught value is 720 by 60 into t value 8 by 2. That equal to here 12 times. So 96 by 2, it is 48 revolutions. So how many number of revolutions made by this wheel before coming to rest when it is acted upon by constant torque in opposite direction, that is n equal to here 48. So what I did here, due to the effect of this constant torque, I calculated average angular velocity 0 plus omega naught by 2. So this average velocity is written as angular displacement by t, and this angular displacement divided by 2 pi, that will give number of revolutions made by this wheel in the given time interval t. So therefore omega naught into t by 2, that will give the angular displacement made by the wheel in the given time interval. So in this time interval, how many number of revolutions made by this wheel can be obtained by dividing this one with 2 pi. So from this we get 720 by 60 into 8 by 2. So from this we get 48 number of revolutions are made by the wheel in 8 seconds before it comes to rest. So why you considered average angular velocity as 0 omega 1 plus omega 2 by 2? Because you are applying here constant torque in opposite to the direction of the motion of the rotating wheel. So in that case only the average value can be taken as omega 1 plus omega 2 by 2. Otherwise this formula is not applicable. Remember that point. Okay. So the number of rotations made by this rotating wheel before comes to rest after the application of constant torque in 8 seconds is here 48 revolutions. So answer is 48 is the answer for question number 2. Next question. A small block is shot in each of the 4 tracks as shown in the figure. Each of the track rises to the same height. The speed with which the block enters the track is same in all cases. At the highest point of the track, the normal reaction is maximum in. So what is the normal reaction? So when the block is projected with equal velocity in all 4 cases as shown below here. So while they entering into the curved path here, indirectly they enter into vertical circular path here. For different curvatures here, radius of curvature is different. So out of all this one here, see in case of B. In case of B here, in case of B, when block moves like this, when it is projected with velocity V, when block moves like this, at this point what are the forces are acting on the block? When it is at highest point, the forces are acting on the block is, one is weight of the block mg, another one is normal reaction by the surface in downward direction n, and centrifugal reaction x on the block is mv square by r. Centrifugal reaction is mv square by r. So at highest point here the balancing equation is mv square by r is equal to n plus mg. We want normal reaction, n equal to mv square by r minus mg. What we want? The maximum normal reaction experienced by the block during its motion on curved part. So that means for maximum, n maximum, here r to be minimum. So mv square by r to be minimum. then only we get maximum value of normal reaction. So out of all this here, so in case of B, R is minimum, here R is. So by taking this curvature here, by taking this curvature here, in this case R is minimum. So in this case R is minimum when compared to here A, B, C and D, because here in this case it is not the curved part, it is the straight part is given. So it is a continuous vertical circular path here. Here it is a linear path is given. It is not the circular path, it is the some parabolic path. So therefore R to be minimum. So because here in order to apply that equation, compulsory the particle or block must move along vertical circular path out of all the given 4 shapes. So this is the path relates to vertical circle. For that reason, at this point normal reaction is represented by mv square by r minus mg. When r is minimum, n will be maximum. So answer is in case of B, n is maximum. So answer is B. So what I did here it is, so I have written the equation for normal reaction at an instant when it reached the highest position of that curved path. So only out of all the 4 options, only in option B only, here there is a possibility of having body moves along vertical circular path. At that path, at the maximum height only, there is scope to write the equation for normal reaction. That is mv square by r minus mg. For having maximum normal reaction, r should be minimum. If such number of curvatures, if such number of circular paths are given, then we have to consider for in which case r is minimum. But here only one option is there, that is B option is there, relates to vertical circular path. For that reason, in case of B only, the particle will experiences maximum normal reaction when it is at highest point of its path. So answer is B for question number 3. Next question. A small particle of mass m is at rest on the horizontal circular platform that is free to rotate about vertical axis through its center. The particle is located at radius r from the axis as shown in the figure. The platform being to rotate with constant angular acceleration alpha. Because of the friction between particle and the platform, the particle remains at rest with respect to the platform. When the platform has reached the angular speed omega, the angle between the static frictional force and inward radial acceleration is. So when particle is kept on horizontal rotating platform, rotates with angular velocity, some omega is given in the data. So as it increases its speed at one particular angular velocity, your particle just ready to slip from the surface of the platform in tangentially outward direction. At that time, we have to calculate the angle between frictional force and the inward radial acceleration. So that we have to find here. So this is the platform. Platform rotates with angular velocity omega. So a particle is placed on the platform like this. So when it is under rotation, so what are the forces are acting on the particle here? One is tangential force MAT, another is centripetal force MAC. Because the rotation of the platform increases from certain minimum value to certain value of omega, at that time this particle is ready to slip from the surface of the platform. At that time, the resultant of these two forces will be like this. This is the resultant force. That resultant force should be balanced by, this is the resultant force, that should be balanced by limiting friction. So indirectly this force to be equated to limiting friction, net force. So this net force will be equal in magnitude to the limiting friction, but in opposite direction. So we have to calculate this angle alpha. Okay, from this triangle here it is alpha. This represents tangential force MAT. This represents centripetal force MAT and MAC here. What is tan alpha from this triangle? Tan alpha is equal to MAT by MA. So AC, MAT is equal to m into at. What is the tangential acceleration of the body when it is under non-uniform circular motion? It is r into alpha by here centripetal acceleration m into r into omega square, because in the data in terms of alpha I have to express the answer. So this alpha, this instead of alpha I consider theta. Okay, so tan theta equal to mr alpha by mr omega square. From this we get r gets cancelled, alpha by omega square. So from this theta equal to tan inverse alpha by omega square is the angle made by this frictional force with inward radial acceleration. So this is the frictional force actually. This is to be balanced by the net force. So due to that, both frictional force and net force are equal in magnitude. For that reason here I considered this normal force. This force tangentially, this is the force, normal force. This is the inward force. So this tangential force is MAT, inward force is MAC, not like this. Okay, this tangential force and inward force, the resultant will be like this. So this resultant force is balanced by frictional force. So from the triangle I consider tan theta, here it is tan theta. So tan theta equal to here alpha by omega square, theta equal to tan inverse alpha by omega square, where in the data alpha is given as angular acceleration, omega is the angular velocity of the rotating platform at that time. So answer is here tan theta equal to tan inverse alpha by omega square. Answer is C for question number 4. So it is also one of the important model question. When rotating platform in horizontal plane at one particular angular velocity, the particle kept on its surface at certain distance, suppose ready to slide, at that moment the frictional force is equal to, what is the limiting frictional force? Fs equal to square root of tangential force plus centripetal force whole square, like this. So root of Ft square plus Fc square is the frictional force acts on the body and the rotating platform at that time. So answer for this question number 4 is theta equal to tan inverse alpha by omega square. So this is all the description is made in the problem. On that basis here directly I have taken this equation. So indirectly the particle is under non-uniform circular motion. So particle or body kept on the rotating horizontal platform is under non-uniform circular motion. So due to that here it simultaneously experiences tangential acceleration and normal or centripetal acceleration. The resultant of these two will be balanced by the limiting frictional force. Then only the particle remains at rest without sliding at the particular angular velocity of rotation. Okay, on that concept, on that idea, I have taken the equations. Okay, so by drawing this triangle, from this I calculated tan theta. We want theta. So what is theta here? The angle made by this frictional force with the inward radial acceleration. That we have to calculate. So tan theta equal to MAT by, here it is mr omega square, from this alpha by omega square, theta equal to tan inverse alpha by omega square is the answer for question number 4. Next question. A point mass m is connected to an ideal spring on a horizontal frictionless surface. The mass is pulled a short distance, then released. Which of the following is the most correct plot of the kinetic energy as a function of potential energy? So a point mass is connected to an ideal spring on a horizontal frictionless surface. It is the point mass here is connected to an ideal spring on horizontal frictionless surface. When it is slightly pulled and released, the point or particle is supposed to be execute simple harmonic motion. During simple harmonic motion, all of you know that the total mechanical energy of the oscillating particle is conserved. So total mechanical energy is conserved. At an instant, the kinetic energy of the oscillating particle is given as Ke is equal to total energy minus potential energy. But we know that kinetic energy of the oscillating particle at a displacement y equal to half m into omega square into a square minus y square. that equal to half m into omega square a square minus half m omega square y square. So, half m omega square a square total energy is constant minus some constant 1 into potential energy. So, if you plot a graph in between kinetic energy and potential energy, it is in the form of y equal to minus mx plus c. So, the nature of the graph plotted between potential energy and kinetic energy is a straight line having negative slope. This is kinetic energy on y axis, potential energy values on x axis, we get a graph having negative slope here. So, negative slope means slope is 1 here. So, whatever the intercept value on y axis, that will be equal to intercept value on x axis. So, the nature of the graph plotted between kinetic energy and potential energy for the point mass connected to the spring when it is under oscillation is a straight line having negative slope. Okay. So, it is a simple question it is. Next question. The potential energy function between two atoms in diatomic molecule can be expressed approximately as follows. Ux as a by x to the power 12 minus b by x to the power 6, where a and b are positive constants, x is the distance between atoms. Then what is the dissociation energy of the molecule? So, in case of this molecule, diatomic molecule, there are two atoms. So, what is the dissociation energy? So, it is the minimum energy required to separate the two atoms. So, dissociation energy is equal to negative value of the potential energy. Negative value of the potential, or generally we know that potential energy is negative. Negative of that negative value will give dissociation energy of the diatomic molecule. So, indirectly the energy required to split this diatomic molecule into atoms is called dissociation energy. So, here first we have to calculate that minimum value of this potential energy. The negative value of the minimum value of this potential energy is called dissociation energy. How you calculate the minimum value of this potential energy when potential energy function is known to you? Simply the first derivative of that potential energy function and is equated to 0 at that respective distance. Here potential energy is minimum, that respective interatomic distance potential energy is minimum, that we have to calculate. Okay, again that value to be substituted in the potential energy function, then you get the minimum value of that potential energy. So, what is the potential energy equation? U equal to a by x to the power 12 minus b by x to the power 6. So, we want du by, it is varies accordance with x. So, du by dx is equal to here a into for x to the 1 by x to the power 12, x to the power minus 12, it is minus 12 into x to the power minus 13 minus of here minus 6 into x to the power minus 7. So, this is the first derivative of the given function with respect to x and it is equated to 0. 0 is equal to, here it is a into here minus 12 by x to the power 13 minus of minus it is plus 6 by x to the power 7. So, from this here we get it into b, the b is there. So, from this it is 12a is by x to the power 13 is equal to 6b by x to the power 7. So, from this 2a by b is equal to x power 6. So, x is equal to 2a by b whole to the power 1 by 6. So, at this value of interatomic distance, potential energy is minimum. So, at x is equal to 2a by b to the power 1 by 6, potential energy becomes minimum. Now, you substitute this value in potential energy function. So, u minimum is equal to, it is, what the basic function here it is a by x to the power 12 minus b by x to the power 6. A by x to the power 12, x is 2a by b whole to the power 6 whole to the power 12 minus b by 2a by b whole to the power 6 and whole to the power, it is 1 by 6, it is 1 by 6, it is 12, it is 1 by 6 whole to the power 6. So, a by 2a by b whole to the power 1 by 6 into to the power 12 minus b by 2a by b whole to the power 1 by 6 to the power 6. So, from this do the calculation. After calculation, you get the answer value as minus b square by 4a. So, it is the minimum potential energy of the diatomic molecule. So, I already told dissociation energy of this diatomic molecule is negative value of that minimum potential energy. So, dissociation energy equal to minus of u minimum. Therefore, it is b square by 4a is the answer for question number 6. So, here what is the dissociation energy of the molecule? B square by 4a is the answer for question number 6. Okay. So, this is the explanation for question number 6. It is also the another basic equation regarding the potential energy of the diatomic molecule. Right. Next question. So, what I considered in the previous question? In the previous question, simply potential energy function is given. Simply have to go for first derivative of that equation with given variable and it is equated to 0. Then you get the value at which potential energy is minimum obtained. That value of x or r to be substituted in the potential energy function. Then you will get the minimum value of the potential energy. The negative value of that minimum potential energy, that will give dissociation energy of the diatomic molecule in this case. So, after calculation we get b square by 4a is the answer for question number 6. Question number 7. A uniform cylinder of radius a and originally has weight 18 Newton. After an off-axis cylindrical hole at a distance of 2a by 5 from center was drilled through it, its weight is 65 Newton. The axes of the two cylinders are parallel and their centers are at same height. A force capital T is applied to the top of the cylinder horizontally. In order to keep the cylinder is at rest, what is the magnitude of this applied force? Closest to 2. Magnitude of this applied force closest to 2. So, a cylinder whose weight is 80 Newton and placed on horizontal surface. So, indirect this weight acts at its center of mass. Okay. This is the cylinder. Its weight is 80 Newton and radius is a. Now, a small hole is made in the cylinder. Small hole is made in the cylinder on its axis, and the axes of these two cylinders are parallel to each other according to given data. When small hole is made, that is cylindrical hole is made in this cylinder in such a way, the axes of these two hole and cylinder are parallel to each other. So, at that time what must be the force required? Force required to keep the cylinder, at rest without rolling. What must be the horizontal force is required at topmost point of the cylinder, so that the cylinder is to be remains at rest without any movement. So, at that time first you have to identify what are the extra forces, what are the forces acts on the cylinder at this stage. Now, I rewrite this diagram as, so the weight of this one, weight, there is a hole here. So, due to that extra weight is there, this is the extra weight. What is that extra weight? Here when hole is made, then weight of the cylinder is given as, 65 Newton. When hole is made, weight of the cylinder is given as 65 Newton. So, here on both side holes, suppose if you made both holes made at both sides of the cylinder. So, what is the weight of the extra hole supposed to made on left side of the cylinder? It's 15 Newton is the weight of the equivalent mass of the hole supposed to imagine on left side of the cylinder when it is acted upon by a force T. At that time, this is the force. So, what are the forces are acting on the cylinder? The weight of the extra weight, the extra weight of the weight in the form of cylinder to be imagined on left side of the cylinder. that is the extra weight. So what is the force applied at its topmost point T? So torque due to this applied force to be balanced by torque due to this extra weight to be imagined in the form of cylinder on left side. So this distance is given. This distance is given as what the distance here 2a by 5 is given in the data. So torque due to this applied force is equal to torque due to this 15 Newton force to keep this cylinder without moving. So this torque tries to roll the cylinder in clockwise, and this torque due to 15 Newton tries to roll the cylinder in anti-clockwise direction. If these two torques are equal in opposite direction, equal but in opposite direction, so net torque is 0, due to that cylinder remains at rest without any rolling. So in this case, torque due to this applied force, so T into the perpendicular distance from center of rotation to the point of application of the force is nothing but radius of the cylinder, is equal to, here force applied is 15 Newton into perpendicular distance from point of application of the force to the axis of rotation, that is 2a by 5. So a gets cancelled, then T is equal to 15 by 5, that is 3 Newton. So what must be the force to be applied on the topmost point of the cylinder so that the cylinder remains at rest? That is 3 Newton is the answer for this question. It is also another different model question regarding this rotatory motion. So see the idea here what I have taken. If some mass is in the form of cylinder is removed on right side, I considered its equivalent mass on left side, having weight 15 Newton. So this 15 Newton acts vertically downward at center of mass of the extra weight. So with respect to initial center of rotation, it is at a perpendicular distance to a by 5. But here force is applied topmost point as T, then perpendicular distance is a. So torque due to this applied force at topmost point is to be balanced by the torque due to this extra weight imagined on left side of the cylinder after hole is made on right side at same distance. So therefore it is 15 into 2a by 5. From this I calculated T value as 3 Newton is the answer for question number 7. So answer is A, 3 Newton. This is another important and standard model question regarding rotation. Next question. Question number 8. A ball is thrown vertically downwards with a velocity root of 2gh from the height h. After colliding with the ground, it just reaches the starting point C. Find coefficient of restitution in this collision. So a ball is dropped, not dropped here, it is thrown down with a velocity root of 2gh from height h. With what velocity it strikes the surface here? So with what velocity it strikes the surface when it is thrown down with the velocity root of 2gh, that V equal to root of u square plus 2gh, u square is 2gh plus here 2gh. So with what velocity it strikes? The hard surface is root of 4gh. According to given data, after colliding the surface again it rebounds to same point C. So here it rebounds with velocity root of 2gh to reach this point C. Okay. So in this case it is A, here it is B, again it is just reaches to point C. So just to reach point C it has to rebound with velocity root of 2gh. We know that E equal to V2 minus V1 by U1 minus U2. So V2, what is V2 value here? V2 is root of 2gh minus V1 is 0. V1 is for surface, and U1 is also here, it is 0, minus U2 value, it is in downward direction, it is in upward direction. So minus of root of 4gh. So from this we get root of 2gh by root of 4gh, that is 1 by root 2. So what is the value of coefficient of restitution in this case? So when ball is thrown down with velocity root of 2gh velocity, when it is at a height small h, then it strikes the floor with velocity root of u square plus 2gh. In place of u I substitute as root of 2gh. From that we get root of 4gh is the velocity of the ball. It strikes the floor, then afterwards it just rebounds rebounds and just to reach point C at which this ball is projected down. So, in order to reach point C, it has to rebound with velocity root of 2gh. So, final velocity is root of 2gh, velocity of projection is root of 4gh. Then the coefficient of restitution in this case is 1 by root 2 is the answer for question number 8. Okay, this is another different model question regarding coefficient of restitution. Next model question. A hoop rolls on a horizontal ground without slipping with a linear speed u. Speed of the particle p and circumference of the hoop at an angle theta is. So, in reality, hoop is nothing but suppose a ring. A ring is rolling without slipping on the horizontal surface. Then what is our question? The speed of the particle at point P, which makes an angle theta with vertical passing through the lowest point of its rolling. So, at that point you have to calculate. So, in this case here, hoop indirectly hoop or ring is rolling without sliding with horizontal velocity u. So, this is the point of contact of the hoop with the ground during rolling here. So, here at this point we want velocity. So, velocity of the point, velocity of the hoop at point P, that we want here. So, we know that when it is under pure rolling without any slipping here at this point velocity is 0. Suppose it is A, velocity at A equal to 0. When body is under pure rolling, velocity of the rolling body with a point of contact is always 0. Okay. Now, velocity at this point, it is to be calculated, Vp to be calculated. Now, here this is the perpendicular distance. So, when it moves from A to P, here the displacement moved by this particle, it is given in the data as theta. So, when particle moves on arc subtended by an angle theta at center, the displacement of the particle is AP. AP is equal to, let r is the radius of the rotation of the particle, then AP is equal to 2r sin theta by 2. AP is 2r sin theta by 2. We want angular linear velocity of the particle at point P. So, linear velocity of the particle at point P equal to omega into this perpendicular distance AP. So, omega into what is the perpendicular distance here AP, it is 2r sin theta by 2. So, that equal to 2 into omega, that is r omega into sin theta by 2. But r omega, when body is under pure rolling, u equal to r omega, therefore, it is 2 into u into sin theta by 2 is the equation for velocity of the point of the hoop which makes an angle theta with the lowest position. So, when hoop is under rolling without slipping, then its center of mass moves with the velocity u is represented by r omega. So, the point where we are going to calculate velocity at that point here, when it moves from point A to P, the linear displacement made by the particle is 2r sin theta by 2. So, how you find the linear velocity of the particle when it is at point P? So, at that point here, linear velocity is calculated by using omega into AP, this perpendicular distance. Linear velocity at point P equal to omega into perpendicular distance AP. Instead of AP, I have written it as 2r sin theta by 2, but r omega is replaced by u. So, therefore, the velocity of the point of the hoop at an angle theta with vertical position passing through lowest point of the rolling is 2u sin theta by 2 is the answer for this question. 2u sin theta by 2. So, for question number 9, answer is A. Question number 9, answer is A. Next question. A body is moving up an inclined plane at an angle of inclination theta with initial kinetic energy k. The coefficient of friction between plane and body is mu. Then work done against the friction before body comes to rest is. So, this is the inclined plane. Body is projected with velocity u and mass m, and it is given as energy E. So, this angle is theta. So, let it comes to rest after crossing through certain distance. Okay. So there will be a frictional force in downward direction. What we want here, the work done against frictional force. Work done against the frictional force before body comes to rest. So it comes to rest. Initially it moves with kinetic energy E. So what is E? E equal to half mu square is the value I considered here. But in the data, body is projected with energy, kinetic energy E at the lowest point of the inclined plane. So when it moves up against the frictional force here, its velocity gradually decreases. Finally, the body comes to rest after covering through certain distance S. So it is the stopping distance at which body is projected from bottom to top of the inclined plane. Now what we want here? What we want? The work done against the friction we want. Simply here we have to apply work energy theorem regarding the projection of the body from bottom to top of the inclined plane. So what is work energy theorem? Work done by conservative forces plus work done by non-conservative forces plus work done by spring forces plus work done by any other internal forces plus work done by any other external forces acts on the body is equal to change in kinetic energy. This is the basic definition of work energy theorem. Work done by all forces acting on the body is equal to change in its kinetic energy. But in this case, only the gravitational force acts on the body, that is conservative force. A non-conservative force is here, frictional force is there. And spring force is absent, internal force, external force are absent. So due to that, work done by gravitational force plus non-conservative force is frictional force. So work done by frictional force is equal to change in kinetic energy. So final kinetic energy is 0, initial kinetic energy is E. So we want work done by frictional force plus work done by gravitational force. What is work done by gravitational force? mg into mg. So here it is not mg here, mg sin theta is the downward force against this one here. Mg sin theta is the downward force. So against this one here it rises to certain displacement S. So that is S, mg sin theta into S. So the work to be done against the gravitational force is equal to minus E. Therefore work done by frictional force is equal to here mg sin theta into S minus E. So mg sin theta into S value, stopping distance. What is the stopping distance here? S is equal to V square by 2 into A. So V square by 2 into what is the acceleration of the body projected up from bottom to top of the inclined plane, that is G into sin theta plus mu cos theta. It is the distance at which this block covers before it comes to rest. V square by 2G into sin theta plus mu cos theta. Therefore it is mg sin theta into, in place of displacement covered by the body, is V square by 2G into sin theta plus mu cos theta minus E. So but half mv square is E into sin theta by here G into sin theta plus mu cos theta minus E. By multiplying this one, E sin theta minus E sin theta. E sin theta minus E, G gets cancelled here, it is. Into G is there, this G gets cancelled. So E sin theta minus E sin theta gets cancelled plus mu sin theta. Therefore, mu E cos theta by sin theta plus mu cos theta. So after calculation, we get the final term as, here it is mu E cos theta by sin theta plus mu cos theta is the amount of work done against the frictional force. So once again, the work done by all forces are acting on the body equal to change in kinetic energy. Here in this case only we consider work done by conservative force is gravitational force, work done by non-conservative force is frictional force, remaining forces are absent. So I considered sum of these two work done is equal to change in kinetic energy. Finally it comes to rest, due to that final kinetic energy is 0 minus initial kinetic energy is given as E. So from this, work done by frictional force is equal to this mg sin theta into S is taken to right side, we get mg sin theta into S minus E, where S is the distance covered by the block on inclined plane before comes to rest, nothing but stopping distance. What is the basic equation for stopping distance? V square by 2a. In place of a I write g into sin theta plus mu cos theta. For body projected up from bottom to top of the inclined plane, its acceleration is g into sin theta plus mu cos theta. So, but half mv square is given as e. Therefore, g into e sin theta by g into sin theta plus mu cos theta minus e is there. So, after calculation g gets cancelled, that is g e sin theta minus of mu e cos theta is there, minus of mu e cos theta is there by sin theta plus mu cos theta. This negative sign represents work done against the frictional force. Therefore, minus mu e cos theta by sin theta plus mu cos theta is the answer for this question. So, answer is mu e cos theta, work done against. So, you have to take plus mu e cos theta by sin theta plus mu cos theta. Answer is D. Mu e cos theta by sin theta plus mu cos theta is the answer. So, for question number 10, D is the answer. Question number 11. Two uniform rods of same length but masses small m and capital M are joined to form L shape. L shape figure shows equilibrium position. Then find capital M by small m. So, the mass of the rods are given small m and capital M, and the angle made by this rod of mass small m with vertical is 60 degree. Angle made by rod of mass capital M with vertical is given as 30 degree. When these L shaped rods are in equilibrium means indirectly the torque acts on the one rod to be balanced by torque acts on the other rod in opposite direction. So, for this linear rod, the weight of the rod acts in vertically downward direction. So, it is mg is the force. For this linear rod here, it is also capital mg. So, torque about this point O, this is the perpendicular distance. For this one, it is the perpendicular distance. This is L by 2 into sin 60 degree. And this distance is L by 2 into sin 30 degree. So, on this rod here at center of mass, its weight acts vertically downward direction. For other rod also, weight acts vertically downward direction as mg here. But with respect to O, about this axis, the torque is weight mg multiplied by this perpendicular distance. When it is L, this distance is L by 2. This distance is also L by 2. So, this distance is L by 2 sin 60, L by 2 sin 60. This distance is also L by 2 sin 30 is given in the data. Now, torque due to this one is, what is torque due to this one? mg into L by 2 sin 60 degree is equal to capital mg into L by 2 into sin 30 degree. So, g gets cancelled, L by 2 gets cancelled, we get m into sin 60 root 3 by 2 is equal to capital M into sin 30 1 by 2. So, 2 gets cancelled, we want capital M by small m, capital M by small m equal to root 3. So, answer is capital M by small m is root 3. So, the simple question it is. So, when two rods are just attached in the form of L shape, if the system is supposed to be in equilibrium, then what is the ratio of their masses is given in the data. So, what I considered here, the system is in equilibrium, immediately I consider net torque acts and the system is 0 about this point of pivot. About this point of pivot on one rod, on left side rod, torque acts in anti-clockwise direction, on right side rod, torque acts in clockwise direction. If these two torques are same, equal in magnitude but in opposite direction, then only the L shaped two rods pivoted point O must be in equilibrium. So, on that basis I consider torques are equal in magnitude. So, therefore, mg into, what is the basic equation for torque? Force multiplied by perpendicular distance. Mg into L by 2 sin 60 equal to, here capital Mg into L by 2 into sin 30. So, by cancelling of the remaining terms, we get mass terms are there. So, m into root 3 by 2 equal to capital M into 1 by 2. From that, capital M by small m equal to root 3 is the answer for question number 11. Next, question number 12. A cannon of mass capital M located at the base of the inclined plane shoots a cell of mass small m in the horizontal direction with velocity v. To what vertical height does the cannon ascend the inclined plane as a result of recoil if the angle of inclination is alpha and coefficient of friction between cannon and plane is mu? So, here you have to assume the proper rough diagram of the description of the given data of the problem. So, what is the rough diagram here? This is the inclined plane. So, cannon is placed like this. This is the cannon. At the bottom of the inclined plane of inclination alpha is given. When it fires a shell of mass m with velocity v. Due to that, here this cannon of mass m, capital M, moves up along the inclined plane like this. It moves up like this. Up to this point it can rise, it comes to rest when it moves up like this. So, in this direction velocity of the cannon is v. Here it is v dash. So, according to law of conservation of linear momentum, when shell is fired with momentum mv, due to that the recoiling velocity of the cannon is supposed to be v dash. So, with that velocity it rises up in backward direction and it ascends along the inclined plane up to certain height. That we have to calculate. H. Let the distance moved by this cannon before it comes to rest is h1. The vertical height raised by the cannon before comes to rest is small h. That h to be calculated. Now, in this case here the coefficient of friction is given as mu. So, this cannon moves on inclined plane having some friction. So, now what we have to proceed? In what way we have to proceed? So, according to given data here, linear momentum is conserved. With what recoiling velocity cannon will move? That we have to calculate it by using law of conservation of linear momentum. So, by using law of conservation of linear momentum, the momentum of the shell is, here it is m into v, that is equal to, here it is minus of m into v dash. So, this negative sign represents already this cannon has to move in opposite direction to the movement of the shell. So, this negative sign is already used. So, v dash is equal to mv by capital M. So, negative. So, it moves in backward direction, already it is taken. Recoiling velocity of cannon. Now, again you apply work energy theorem. In this case. So, according to work energy theorem, here also work done by frictional forces plus work done by gravitational force is equal to change in kinetic energy. So, work done by frictional forces. What is the frictional force? That what we have to calculate here? See here, what vertical height does the cannon ascends? So, at the same time, with what energy it moves here? With what energy from the base of the inclined plane? Kinetic energy half m into here v dash square. All the kinetic energy of the cannon converted into potential energy when it rises to certain height along with work done against friction. So, here that is equal to, here work done against friction is equal to, on inclined plane work done is mu mg cos alpha into the distance moved by the cannon on inclined plane before it comes to rest is h dash plus potential energy of the cannon is mgh. So, this is the work done against the frictional force plus here potential energy of the cannon. So, therefore, all the kinetic energy of the cannon before it comes to rest while moving or while ascending the inclined plane converts into work done against frictional force plus potential energy, because cannon is supposed to rise to a vertical height h from the base of the inclined plane. So, in this case mu mg into cos alpha into what is h dash? It is alpha, it is h, it is h dash. So, from this sin alpha is equal to h by h dash. So, h dash is equal to h by sin alpha, where h dash is the distance moved by the cannon. Distance moved by the cannon before comes to rest is the h dash. So, therefore, it is h dash is h by sin alpha plus mgh is equal to half m into, instead of v dash we write m square v square by capital M square, because v dash whole square, v dash is mv by capital M. So, m square v square by capital M square. So, from this here, so mu mg cos alpha by sin alpha, you multiply with sin alpha on both sides, we get 1m gets cancelled, m square v square sin alpha by 2 is equal to, here it is cos alpha mu mg cos alpha, h is there, h into mu mg cos alpha plus mg, h is there, mg into sin alpha. So, what we want here, h is equal to m square small m square v square sin alpha by 2 into, here it is mg is also taken as common factor, it is 2 into mg into mu cos alpha plus sin alpha. So, it is the height at which cannon rises in backward direction after firing a shell with a linear velocity v. Once again, here when cannon fires a shell of mass m with velocity v, then let it moves in backward direction with velocity v dash. With this velocity, it has to ascend along the inclined plane until it comes to rest. So, during this attempt, it covers a distance h dash along the inclined plane, but this is the vertical height raised by the cannon before it comes to rest. So, therefore, here it is h dash is the displacement made by this cannon before comes to rest on inclined plane. H is the vertical height raised by the cannon before it comes to rest with respect to the initial position of the firing of the cannon. So, due to that, here what we have to find here, h value to be calculated, h value to be calculated. So, according to the law of conservation of linear momentum, I calculate velocity. So, with what energy here cannon moves up, all that energy will be wasted in overcoming the frictional force, and remaining part to be converted into potential energy. So, according to, here it is, according to the conservation of energy in this case, whatever the energy it is given to the cannon in firing the shell, that will be used in two parts. One part is work done against frictional force, remaining part to raise this body to certain height in the form of potential energy. So, mu mg cos alpha is the frictional force of a body on inclined plane into the displacement moved by cannon before it comes to rest is h dash. H dash is h by sin alpha plus mgh. So, after taking the terms here, in this case, we get up to what vertical height this cannon rises on inclined plane in backward direction, that is m square v square sin alpha by 2 mg into mu cos alpha plus sin alpha is the answer. So, here it is m square v square sin alpha by, here in this case one m is there, see one more m is there, here already m is there. So, it is m square, already one m is there, here 2m, so 2m square g. So, m square v square sin alpha by 2m square g into sin alpha plus mu cos alpha, this is the answer. M square v square sin alpha by 2m square g into sin alpha plus mu cos alpha is the answer for question number 12. So, it is the another standard model question, consists lot of mathematical considerations, and also here by applying law of conservation of energy along with the law of conservation of linear momentum. Okay. So, now the h value is calculated as m square v square sin alpha by 2m square g into sin alpha plus mu cos alpha is the answer for this question. So, answer is A for question number 12. Next question. when someone jumps, one always bends one's knees to lower the center of mass of the body by 40 centimeters, then jumps up. So, one who lowers by knees like this, one who lowers by knees through a distance. So, a man whose center of mass lowers by 40 centimeter, one who lowers by knees through a distance 40 centimeter and then jumps up. One can usually reach a height 50 centimeter above. During jumping, he usually reach a height of 50 centimeter above your normal height. Then above normal height, it will be raised by 50 centimeters. Then what will be the shift of center of mass of that man during its jumping by lowering its knees through a displacement 40 centimeter? Indirectly, the rise of center of mass of the man is delta H, that equal to here 40 plus 50 centimeter, that equal to 90 centimeter. This is taken as H, capital H. So, now what we want here? What is the work done by a man of 9 kg? Work done by a man of 80 kg it is. So, work done in rising, it is the center of mass to a displacement 90 centimeter is mgh, mg into h. Mass of the man is 80, g value is given as, here it is 10 into 90 centimeter, 90 into 10 power minus 2. So, after that here we get, it is 10 power minus 2, these two zeros gets cancelled, 720 joules. So, 720 joules is the value of work done by a man, in jumping to a usual height of 50 centimeter by bending its knees to a displacement 40 centimeter initially. So, overallly its center of mass rises by 90 centimeter during jump of a man during its usual attempt. So, in this case, work done in lifting its center of mass by 90 centimeter is mgh. So, rise of center of mass of that man during its attempt is here 90 centimeter to be converted into meters. So, 90 into 10 power minus 2. After calculation, we get 720 joules is the amount of work done by a man during its attempt. Next question. A block A is placed over a block B having mass m and 2m respectively. Block B is resting on a frictionless surface and there is a frictionless surface and there is friction between block A and block B. The system of blocks is pushed towards a spring with a velocity v0 such that A does not slip on B by the time the system comes to momentarily rest. Then correct statement is, here two blocks are given placed one over other and block B is provided with velocity v0 towards a spring, and the total system of A B block system momentarily comes to rest after some time. Now, which one is correct? Work done by frictional force on A, work done by frictional force on B, work done by spring on B, work done by friction on A. So, that we have to identify. So, when two blocks, when it is projected with velocity v0, it is block A, which one is block A, which one is block B? Here upper one is block A, lower one is block B, its mass is m, its mass is 2m. So, when it is projected with velocity v0 towards a spring, a force constant k, I do not know, it is not given. Okay. In this case, when it is projected with velocity according to given data, both blocks combinedly move together. Combinedly move together means here work done by on block A. On block A here simply apply work energy theorem. Work done by A. So, the work done by A on B. Work done by A on B, at the same time work done by B on B. B on A, work done by A on B, and work done by B on A also to be taken into consideration. So, according to work energy theorem here, work done by frictional force on A, that is equal to change in kinetic energy of the block A. That is, change in kinetic energy is initially 0 minus kinetic energy is half m into v0 square. So, work done by B on A, indirectly work done in keeping the block A in contact with B against the frictional force is equal to minus half m V naught square. Next, on block B, we know that work done by frictional force on block A plus work done by frictional force on block B must be 0, because work done by A on B plus work done by B on B must be always 0. Work done by frictional force in between A and B, suppose is there 0. Indirectly, it indicates work done by frictional force on A by B plus work done by frictional force on B by A. The sum is always 0. But you know that work done by frictional force on A by B. So therefore, work done by this one is minus half m V naught square is equal to here work done by frictional force on B. So therefore, work done by frictional force on B is equal to half m V naught square. Half m V naught square. Now for total system. For total system here. So when both blocks combinedly move together and strikes the spring, then the change in here also you apply work energy theorem in this case. So therefore, work done by here frictional force on B plus work done by spring force is there. Work done by spring force is equal to change in kinetic energy. 0 minus kinetic energy is half into mass of the block is 2m into V naught square. So this is the change in kinetic energy of the AB block system when it strikes the spring. This spring strikes only block B. So due to that here work done by frictional force on block B plus work done by spring force is equal to change in kinetic energy. So work done by what we want here, work done by spring force is equal to, this one is taken to that side, from this we get minus half mv square, minus half mv naught square minus 2 gets cancelled mv naught square, that equal to minus of 3 by 2 mv naught square. So work done by frictional force on block B, work done by spring force on block B, spring force on block B equal to minus 3 by 2 mv naught. Work done by frictional force on block A is equal to minus half mv naught square. Work done by frictional force on block B is equal to plus half mv naught square. Work done by spring force on block B is equal to minus 3 by 2 mv naught square. On that sense, we have to take the answer. See, work done by frictional force on A is 0, wrong. Work done by frictional force on B is plus mv naught square, it is given wrong. First one is wrong, second one is wrong. Work done by spring force on B is minus 3 by 2 mv naught square. Yes, it is correct. Work done by friction on A and B is 0. Work done by friction on A and B. So it is also correct. Work done by frictional force on A and B. So it is not separately. Work done by frictional force on both on the system A and B is 0. Okay. So work done by spring force on B is minus 3 by 2 mv naught square. Work done by friction on A and B of a system is 0. So due to that here, by considering this as a system, it is also correct answer. So there are two answers for this question number 14. So this is the explanation for question number first. I considered work energy theorem for block A. Work done by frictional force on block A equal to change in its kinetic energy minus half mv naught square. Next, on B, work energy theorem, work done by frictional force on A plus work done by frictional force on B, sum of these two values must be always 0. If A block slides over block B, then work done by A on B is equal to work done by B on A. The sum of these two values is equal to 0. Therefore, it is work done by frictional force on A is given as minus of half m into V naught square equal to minus of work done by frictional force on block B. So work done by frictional force on block B is equal to half m V naught square. Now for total system, here what are the forces are acting on total AB block system when it is projected with velocity V naught towards a spring. So only block B strikes the spring here. So due to that here, the work done by frictional force on block B by A plus work done by spring force is equal to change in kinetic energy of the block B. So half into m, mass of the block B is 2m into velocity is V naught square. So from this we get minus mv naught square. For this work done by frictional force on B is half mv naught square is taken to right side, we get minus half mv naught square. From that we get work done by spring force on block B is equal to minus 3 by 2 mv naught square is the answer for this question. Next, question number 15. A ball of mass m is released from the top of the smooth movable wedge of mass m. When ball collides with the floor, the velocity of the wedge is v. Then maximum height attained by the floor is, maximum height attained by the ball on the floor is, maximum height attained by the ball on the floor. That you correct this question. Okay. Then maximum height attained by the ball on the floor is, that we have to calculate. Neglect any at lower edge of the wedge. So when ball is released from top of the smooth movable wedge, when ball comes down, what happens? This wedge, ball moves towards right side. When ball strikes the floor here, when ball strikes the floor at this point, is certain velocity, but in this direction it strikes the floor. Then it has horizontal component of velocity, vertical component of velocity. So this is velocity of the ball along horizontal direction after striking the floor. This is the velocity of the ball along vertical direction after striking the floor. But according to given data, let this wedge of same mass moves with velocity v. So when ball collides the floor here in this direction, so but it has to be constrained to move along horizontal direction. It has to constrain to move along horizontal direction because both masses are same. So all of its velocity to be constrained to move along horizontal direction in pushing this small m towards rightward direction with velocity v. So due to that its velocity will be doubled. So horizontal component of this velocity is equal to 2 times that of velocity of this one, 2v. But this angle is 45, here also it is 45. So this Vy value is also, because when it is 45, horizontal component of velocity is equal to vertical component of velocity of the ball, that is also 2v. Okay. So when it strikes on this surface, when ball strikes indirectly with vertical velocity Vy equal to 2v, then it rises to vertical height. It is also because ball collides with the floor. When it is a perfect elastic collision, then only the horizontal component of velocity will be double of the velocity of the, here it is wedge. So due to that, here it rebounds with velocity 2v. That is the vertical component of velocity is 2v. What we want? What is the maximum height reached by the ball? So maximum height reached by the ball, h equal to u square by 2g. For body projected vertically upward with velocity u, then maximum height reached by it is u square by 2g. So in this case, the maximum height reached by the ball, here it is v square, that is vy square by 2g. In place of vy I write 2v, that is 4v square by 2g. So from this it is 2v square by g is the maximum height reached by the ball in vertical direction. So once again, when ball is allowed to release on inclined plane from top to bottom, if it strikes the floor elastically, due to that here, and because smooth surface is given, so due to that there is no loss of energy of the ball. So there is no loss of energy of the ball. So due to that here, the motion of the ball is constrained to move along horizontal direction during this elastic collision. But according to given data, if this wedge moves with velocity v, then compulsory the ball's horizontal velocity must be double of this velocity because masses are same. It is given. All this velocity to be constrained like this. So therefore it is 2v. Indirectly it represents vertical component of velocity is also 2v because this angle is given as 45 degree. So tan 45 equal to vy by vx. Vy is 2v, vy by vx is 2v. Angle is 45. So from this vertical component of velocity is also 2v. So indirectly this ball rises vertically upward with velocity 2v. Then vertical height raised by the ball is v square by 2g, that is vy square by 2g, that is 4v square by 2g. So 2v square by g is the vertical height reached by the ball after collision at this point. So answer is 2v square by g is the answer for question number 15. Next question. Question number 16. A rigid body oscillates about point O. The distance between O and center of gravity is L. The radius of gyration is capital K. Then what will be the equivalent length here? A rigid body oscillates about point O. The distance between point O and center of gravity, this is center of gravity, this distance is capital L. The radius of gyration of the rotating body is K. Then what will be its equivalent length? So indirectly this problem relates to physical pendulum. So what is the time period of the oscillating physical pendulum? T equal to 2 pi into root of here it is I by I about O by here it is mg into distance between point of suspension to center of gravity, that is L. What is the moment of inertia of this rod about an axis passing through point O and perpendicular to its plane? But it is 2 pi into square root of I naught it is mk square plus this distance ml square by mg into L. So you divide with L, m and m gets cancelled, you divide with mgl. So 2 pi into root of mm gets cancelled, k square by L plus L by g. K square by L, mm gets cancelled, by g is there, plus by dividing with L you get L square by L you get L. So this is the, when it is compared with the standard form of T equal to 2 pi root of L by g, this effective length or equivalent length of this physical pendulum is L effective, that is equal to K square by L plus L is the answer. K square by L plus L is the answer for question number 16. See the data, K square by L plus L, answer is D. So what is the time period of the physical pendulum? 2 pi root of I naught by mgl. What is I naught? Moment of inertia of this physical pendulum about an axis passing through point of suspension O is I equal to I naught plus m into this distance square, mx square. This I naught is written in terms of radius of gyration as mk square plus ml square by mgl. So by keeping g in the denominator, by cancelling with m and also L, we get k square by L plus L by g. So from this it is compared with the standard form of T equal to 2 pi root of L by g. From this we get equivalent length of the physical pendulum is k square by L plus L is the answer for question number 16. Question number 17. Suppose all the people in the world line up at the equator and all starts running at speed v relative to the surface of the earth along the equatorial circle. The initial angular velocity of the earth is omega naught, moment of inertia of the earth is IE, I suffix E it is IE, moment of inertia of the all people is IP, radius of the earth is capital R. Then see the options. There is no change in angular velocity of the rotation of the earth. The people run due east, change in angular velocity of the earth will be, people run due west, change in angular velocity, the people due west, change in angular velocity of the earth will be. So indirectly, during running of the people along the line of equator, we have to calculate the angular velocity of the earth. From that we can calculate change in angular velocity of the earth. If all the people in the world are supposed to line up, all the people in the world are supposed to line up along line of equator. Okay, initially this rotates with angular velocity omega naught. When people line up along the equator and supposed to move with relative velocity v relative velocity with respect to the center of the earth here, then in this case before movement of the all the people lined along the line of equator, the angular momentum of the earth people system is equal to angular momentum of the earth people system after these people are moving with certain relative velocity v relative along the line of equator. So angular momentum before movement of the people is equal to angular momentum after movement of the people along line of equator. So before movement of the people, angular momentum is, what is angular momentum? Here it is I naught that is the velocity. Here it is I dash into omega dash initially. So, these people will moving with a linear momentum. So, Ip into what is Ip into omega of the people relative. Okay. So, Ip into I omega, so I dash omega. So, omega of the people, Ip into omega of the people is equal to I dash into omega dash of the earth people system. Moment of inertia I dash is the moment of inertia of the earth and people system. Here only moment of inertia of the people into angular velocity of the people. Okay, that we want. So, from this omega dash is equal to Ip into omega p by I dash. So, Ip moment of inertia of the people is given as Ip. What is angular velocity of the people? So, these people are moving with relative velocity, v relative with respect to axis of rotation. So, v relative velocity of all the people equal to r omega, r into omega relative. So, omega relative is written as relative velocity of the all people with respect to axis of rotation of the earth. So, therefore, in place of omega p I write v relative by r into moment of inertia of the total system of earth and people, that is moment of inertia of the earth plus moment of inertia of the all people. So, this is the angular velocity of the earth people system when all people in the world are line up along equator and moves with relative velocity v relative. This is the equation. So, if these people, we know that earth rotates from west towards east, the rotation of earth is from west towards east. If this people rotates from east towards west, then angular velocity is less than its original value. If people run due east, then angular velocity, net angular velocity is equal to omega naught minus omega dash, that equal to omega naught minus, what is omega dash here? It is Ip into v relative by capital R into IE plus Ip. So, if the people runs in the direction of west to east, then we have to consider omega naught plus omega dash. If people run due east, means they are running from east towards west. So, in that time, at that time, here angular velocity decreases to certain value. So, angular velocity decreases to certain value when compared to its initial value omega naught. So, that change in angular velocity is nothing but delta omega, change in angular velocity. So, due to the rotation of the earth along with the movement of all the people lined up along the equator, then angular velocity decreases by an amount omega naught minus Ip v relative by capital R into IE plus Ip. See, in the same case, if people line up due west, line up along the equator and move due west, then it to be added. Okay, so on that sense, you take the answer. So, here people, first one is wrong, second one is people run due east, change in angular velocity of the earth is omega naught minus IPV relative by R in right, this is correct. People run due west, it is wrong. So, here plus is to be taken. People run due west, change in angular velocity, it is also minus is not correct, so it is wrong. Out of all this, answer is B. Answer is B for this question. Okay. So, question number 17, answer is B. Important and standard model question it is. So, what I considered before and after movement of the people along line of equator, I consider the conservation of angular momentum, because there is no external torque acts on the system of this people and earth, because people are itself the integral part of the earth system. For that reason, here there is no external torque acts on the people and earth system. For that reason, here which physical quantity is conserved, angular momentum is conserved. So, I consider law of conservation of angular momentum. Question number 18. A ball rolls without slipping on the horizontal surface and then moves up the inclined plane shown below if the height attained is h1 and h2 with sufficiently rough track and with smooth track. For sufficiently rough track, now what is the energy here? Half mv square plus half I omega square all the total energy of the ball is converted into here potential energy mgh1. If it is smooth track, there is no rolling of the body. For smooth track, there is no rolling of the body, only it is having linear kinetic energy of mv square equal to mgh2. So it is for rough surface and it is for smooth surface. So in which case height is more. So h1 to be, this term is calculated on the basis of addition of these two terms. This h2 to be calculated on the basis of only this single term. So due to that, h1 is more than h2. When body rolls and moves on rough inclined plane, then it rises more height when compared to body rolls, body moves and slides on smooth surface. On smooth surface, it doesn't roll, it slips and moves up to a particular height, h2. So therefore, h1 is more than h2 for question number 18. So answer is C for question number 18. h1 is more than h2, that is on rough surface. Here it needs more energy. So due to that, height will be more. Question number 19. A conical pendulum consists of a slender bar AB of length L and mass capital M. If it rotates with constant angular velocity omega, then the value of cos alpha will be. So when slender bar is under rotation with constant angular velocity omega, we know that here about this axis of rotation, at each and every point, that particles at the cylinder at different positions will experience different centrifugal forces, because radius of rotation is different for different particles. So because this radius is different for different position of this cylinder bar under rotation. So it is a problem relates to variable centrifugal reaction. So due to this central bar here, what are the forces are acting on the cylinder bar here? So when bar is pivoted and allowed to rotate, body is pivoted and allowed to rotate about this axis, then it rotates and moves on horizontal circular path. So what are the forces are acting on the cylinder bar? First you have to identify. One is always weight of the cylinder bar acts in vertically downward direction, that is weight acts in vertically downwards, and the centrifugal reaction acts radially outwards, centrifugal reaction mr omega square. So this weight is different at different points. At this point it is mg, at this point it is the weight only, at this point this part of the weight only, at this point this part of the weight only. So here weight is different at different points on the cylinder rod. At the same time, it experiences different centrifugal reactions at different points on the cylinder rod when it is under rotation about an axis passing through point of pivot. So due to that, here it is a problem relates to here variable centrifugal reaction and variable weight of the cylinder rod at different positions. So for this rod to be in equilibrium at this angle represented in the given data as alpha, according to given data, at this angle the rod is said to be in equilibrium. So when it is under rotation, at the radius of rotation, suppose it is r, at this radius of rotation, rod is in equilibrium by making an alpha with vertical. So indirectly we considered at the angular position of alpha, rod is said to be under equilibrium. Now what are the forces are acting on the cylinder rod here? So consider one of the elementary strip of length dx and mass dm, suppose it to be considered at a distance x from axis of rotation. Now centrifugal reaction on this elementary strip is dm into x into omega square, and the weight of this elementary strip is dm into g. So this is the angle made by this elementary strip with vertical under rotation, rod is under rotation. Now what is the torque due to this centrifugal reaction? Torque due to centrifugal reaction is force multiplied by this perpendicular distance. Torque due to weight of this elementary strip is force multiplied by this perpendicular distance. So for this here, this is alpha, this is x, so it is x sin alpha this is x cos alpha. So, torque due to this weight is to be balanced by torque due to centrifugal reaction. So, torque due to weight is dm into g into perpendicular distance, it is x sin alpha, equal to torque due to centrifugal reaction, it is dm into r it is. So, dm into, in place of it is r, this distance is r. So, mr into omega square into perpendicular distance is x cos alpha. So, from this here it is dm into r is again, what is r here? This is the radius. R equal to, here it is x sin alpha into here x cos alpha is equal to dmg into x sin alpha. Because here as x increases, centrifugal reaction and weight also increases. Due to that, x is the variable quantity. So, do not cancel x on both sides, only sin alpha gets cancelled, dm gets cancelled. So, g is there, it is mr omega s, g is there. So, gx is equal to dm gets cancelled here, it is x square cos alpha. So, g into x into, I multiplied with the dx on both sides, x square into dx into cos alpha. By integrating on both sides within the limits 0 to L, we get g into, for x dx integration is x square by 2. So, it is L square by 2 is equal to, for x square dx integration is x cubed by 3, that is L cubed by 3 into cos alpha, okay, into omega square is there here, mr omega square is there, into omega square it is. So, from this here L square gets cancelled. What we get here? It is GL square by 2 equal to, here it is L cubed by 3 cos alpha into omega square. So, one L square gets cancelled. So, from this what we want here? Cos alpha equal to 3g by it is L into omega square. So, cos alpha equal to 3g by L into omega square, this is the answer. So, what we considered here? So, when slender rod is under rotation, if the angle made by the slender rod, slant rod with the vertical passing through x of rotation is supposed to be alpha, at that position the rod is said to be in equilibrium, then the torque due to the centrifugal reaction on the rod at different positions to be balanced by torque due to weight of the rod at different positions. Because as x distance increases from x of rotation to the respective points, a radius of rotation also increases. Due to that, centrifugal reaction also varied. At the same time, weight at the different positions also it is different. For that reason, I considered one of the elemental strip of thickness dx, mass dm at a distance x from x of rotation. This is the x of rotation. Okay. So, in this case here, centrifugal reaction on this elemental strip is mr omega square. At the same time, weight of this one is dm into g in vertically downward direction. The torque due to this centrifugal reaction is balanced by torque due to the weight on the slender rod under rotation at this particular angle in equilibrium. Therefore, weight into perpendicular distance is x sin alpha equal to mr omega square into perpendicular distance is x cos alpha. So, dmg into x sin alpha equal to dm into, instead of r I write, this is the radius of rotation, r equal to x sin alpha into x cos alpha into omega square is there. Okay. So, x square into cos alpha into omega square equal to, here it is gx, but here x is variable. As x varies, then only weight varies, here centrifugal reaction varies. Do not cancel out, strike out x. Okay, you put x as it is and multiplied with the dx on both sides. Integral of gx dx equal to integral of x square dx into cos alpha into omega square. So, from this after calculation we get cos alpha equal to 3g by L into omega square is the answer for question number 19. So, it is a other different model question. Here if you cancel x, you will not get answer because x is the variable quantity. Here you have to multiply with the dx on both sides for this, because that is the point here why consider small elementary strip. For the small elementary strip we considered here in terms of x it is. So, if x varies, then only the centrifugal reaction and also this weight of the elementary strips also increases along with the x value. Do that, don't strike off x on both sides. You keep x as it is and multiply it with dx and do integration within the limit 0 to L length of the rod. Then you get finally here cos alpha value at equilibrium position is 3g by L into omega square. So, at this angular velocity of the slender rod, so at an angle alpha of a value of cos here, the slender rod is under rotational equilibrium. So, that is 3g by L into omega square is the answer for question number 19. Question number 20. A uniform sphere of mass m and radius small r is placed in a corner with its initial counterclockwise angular velocity omega naught as given. If mu equal to 1 for both surfaces, then time required for the sphere to come to rest. See, the sphere is under rotation when it is placed near the two vertical walls. So, it is in counterclockwise direction, it is having here angular velocity omega. At this point of contact here, it tries to rotate in this direction. So, therefore, frictional force will be in upward direction. At this point of contact, it tries to rotate towards right side. So, at this point, so frictional force is in this direction. It is F1, it is F2. Okay. So, at this point, frictional force on horizontal surface equal to mu into normal reaction at this point of contact is suppose N1, mu into N1. At this point, normal reaction point of contact is N2, frictional force is equal to mu into N2. Now, what are the forces? Weight of this one acts vertically downwards mg. So, these are the forces are acting on the sphere. Initially, it is under rotation in anti-clockwise direction, placed at this corner of the two perpendicular rigid supports. Then it continuously rotates and finally it comes to rest after some time. So, at the time of rotation, it exerts some normal reaction. At this point, due to that this wall exerts normal reaction on the rotating sphere as N2. At this point of contact, normal reaction exerted by this horizontal wall is N1 in upward direction and weight of this one acts in downward direction. These are the directions of the frictional forces on the rotating sphere in counterclockwise direction. Now, and it is in equilibrium because it does not move. So, due to that here the net force on the system is 0. It is in translational equilibrium. Therefore, F2, what is F2 here? It is mu N2 plus mu N2 in upward direction plus N1 is equal to mg. Mu N2 frictional force plus N1 that equal to mg. Now, in horizontal direction, mu N1 is balanced by N2. So, you replace here N2 as mu N1. Mu N1 is balanced by, here it is N2. So, you replace mu into N2 as mu N1 plus N1 is equal to mg. You take N1 as common factor, mg by 1 plus mu square. So, but mu value is given as 1. Then normal reaction at this point at this point of contact is mg by 2. 1 plus 1 mg by 2. Now, what we want here? The time taken by this one before comes to rest. So, during this rotation here, so here torque due to, so when it rotates like this, torque due to frictional force will be in this direction. Torque due to this frictional force will be in this direction. So, this sphere attains angular retardation due to the torque due to this frictional forces. For this reason, here it is So, torque due to this frictional forces will give angular retardation. So, net torque is F2 into perpendicular distance is R plus F1 into perpendicular distance R equal to I alpha. So, F2 is here it is mu mg into R plus here F1 is also F1 and F2 values are, what is F1? Mu n1, F2 is mu n2 plus F1 is mu n1 into R is equal to I value. What is I value here? Sphere is there. So, 2 by 5 mr square into alpha, but it is negative. Okay. Now, in this case, so mu n1 and n2 values are there. Mu is taken as common factor. N2 value is, what is n1 here? Mg by 1 plus mu square. So, mu into n2 plus n1 is mg by 1 plus mu square is equal to 2 by 5 mr square into alpha. So, from this we can calculate mu also, alpha in terms of mu, but in this case here I considered frictional force. Okay, frictional force is F2R plus F1R equal to I alpha. So, mu n2 plus mu n1 into R equal to 2 by 5 mr square into alpha. See the question here, what we want, the time required for sphere to come to the rest. Here we have to consider angular velocities. So, here in terms of angular velocity we want to express the answer. So, first we have to calculate alpha value. So, for this frictional force here mu1 equal to mu2, n1 equal to, we know that relation between n1 and n2. So, n1 equal to mg by 2, So, therefore, from this here mu is 1 means mu n1, F2 equal to mu n2. It will be little bit different when compared to these two equations. So, on that basis here I write the torque equation in terms of alpha. What is torque? Basically, torque is equal to F2 into R plus F1 into R is equal to I alpha. So, from this I equal to 2 by 5 mr square into alpha equal to F1 is mu n1 plus mu n2. From this we calculate alpha just like in the previous point. Okay, when you know alpha value, what is the final angular velocity? Omega equal to omega naught. This is negative, you will get negative because minus is there. So, when you know what is the final angular velocity, omega naught minus alpha t plus alpha t, you get alpha is negative, but this omega is 0 according to given data. So, from this 0 is equal to omega naught minus alpha t. So, alpha t equal to omega naught. So, from this t is equal to omega naught by alpha. Okay, you substitute this alpha value in this equation, then we get a t value as, but the t value here it is, so omega naught by omega naught by r. I will check the answer of that question after calculation. So, after calculation you get 5g by r. So, 5g by 2r. 5g by 2r you get from this omega naught value after calculation, you get that is t equal to 2 omega naught r by 5g. So, do substitute the values of n1 and n2, in this equation, then you get alpha value as minus 5g by 2r. Then again you substitute this value in this equation, 0 equal to omega naught minus alpha t equal to omega naught, t equal to omega naught by alpha. So, at the same time linear velocity also becomes 0, because here there is no linear movement. There is a linear moment of the sphere when compared to the previous problem. For that reason only I considered equation relates to rotatory motion of the sphere. So, due to that here I considered after what time it comes to rest. After what time it comes to rest means, so its angular velocity becomes 0. So, omega naught minus alpha t. You substitute n1 and n2 values in this equation, n1 and n2 values in this equation, then you get here it is alpha value as minus 5g by 2r, that is equate substitute in the equation omega equal to omega naught plus alpha t. From this we get t value as 2 omega naught r by 5g is the answer for this question. Okay. So, answer is 2 omega naught r by 5g. D is the answer for question number 20. A is wrong, B and C are wrong. D is the correct answer for question number 20. So, answer for the previous question is D, 2 omega naught r by 5g. Next question. A uniform circular disc is placed on the rough horizontal surface, has initial velocity v naught and angular velocity omega naught as shown in the figure. Disc comes to rest after moving certain distance. It is a problem opposite to first question. Today's module first question it is. So, disc is initially placed and rotates in and counterclockwise direction, placed on rough horizontal surface. Then as it rotates, as it rolls and moves here, in this case it tries to rotate in anti-clockwise direction. So, frictional force will be towards leftward direction. So, but it rotates and moves until it comes to, see here, the disc comes to rest after traveling to certain distance. It comes to rest, means initial final velocity is 0, final angular velocity is 0 after covering through this distance. So, it is due to frictional force which acts on the disc in opposite direction. Therefore, this frictional force provides the retardation for the rolling disc during its horizontal motion. Therefore, it is a minus ma. This frictional force is mu mg is equal to minus ma. From this a equal to minus mu g is the linear acceleration of the disc under rotation before coming to rest. Now, force equation is over. Now, torque equation. Due to this force here, torque acts on the disc is torque acts on the disc is tau equal to, here it is I alpha. So, this torque is due to frictional force F into R equal to I alpha. This frictional force is mu mg into R is equal to, for disc moment of inertia, mr square by 2 into alpha. So, here m gets cancelled, r gets cancelled, alpha, and this angular velocity also becomes 0 after travelling through certain distance. So, it is also, so this torque also opposes the direction of rotation of the disc placed on horizontal surface. So, due to that it is also minus. So, alpha equal to, it is mu g 2 mu g by r is the equation for alpha, but it is retardation, minus 2 mu g r. Okay. So, what is the final velocity of the disc after t seconds? V equal to v naught plus at, v naught plus at, but the initial velocity is given. See, the initial velocity is v naught is given. So, v naught minus a is mu g into t equal to 0. So, from this mu g t is equal to v naught. Now, in a similar way for angular velocity, omega equal to omega naught plus alpha t, omega naught is 0, sorry, omega is 0 after t seconds. So, omega naught plus alpha is minus 2 mu g r into t. So, therefore, here it is omega r omega naught is equal to 2 mu g into t. In place of t, it is equation 1, it is equation 2. So, 1 is substituted into 2 mu g by 2 mu g into t value is, what is the here? V naught by mu g. So, that equal to r omega naught is equal to mu g gets cancelled, 2 v naught. So, from this we want r omega naught by v naught value, that equal to 2. So, what is the value of r omega naught by v naught value? That is equated to 2. So, what is the difference between previous problem here? In previous problem here it is under rotation in counterclockwise direction, it was obstructed by frictional forces at 2 point of contacts. But in this problem, when disc is under rotation in counterclockwise direction, supposed to place on laterally and horizontal rough surface, then it has to move with linear retardation, and at the same time with angular retardation, then only its velocity comes to rest. Indirectly its final velocity and the final angular velocity is 0, but its initial linear velocity is given as v naught, initial angular velocity is given at omega naught. So, what I considered? I considered force equation and the torque equation. At the same time, final velocity, linear velocity equation, final angular velocity equation. So, whenever body is in rolling on horizontal surface, you have to consider these 4 equations for immediate calculation of the answer. Okay. So, for force equation here, during this rolling in anti-clockwise direction, so frictional force is towards left side. So, it acts opposite to the direction of the rolling disc. For that reason here it attains a linear retardation. So, Fs equal to minus ma. So, in place of Fs I write mu mg equal to minus ma. So, a equal to mu g. In a similar way here torque equation is, torque acts on the rolling cylinder or disc is here I alpha. But here this torque also which acts opposite to the direction of rotation of the disc on the horizontal surface. Due to that it attains angular retardation alpha, minus alpha. So, therefore, minus mu mg into frictional force is minus mu mg into r equal to mr square by 2 into alpha. From that we get alpha equal to minus 2 mg by r. Now, linear equation of the disc after t seconds, it becomes 0, v equal to v naught plus at. V naught instead of a I write minus mu g into t equal to mu g t equal to v naught, called as equation 1. Regarding angular motion, angular velocity after t seconds equal to omega naught plus alpha t, omega naught minus alpha is minus 2 mu g by r into t, equation 2. So, by equating this one, r omega naught is equal to 2 mu g into t, but t is replaced by, from the equation 1 as t equal to v naught by mu g. So, mu g gets cancelled, r omega naught equal to 2 v naught. From this what we want according to given options, r omega naught by v naught equal to 2 is the answer for question number 21. So, answer is 2 is the answer for question number 21. So, it is another standard model question for JEE mains. Thus, previous question, 20th question and 21st question and first question. These are the important models regarding rolling of the body. Next, question number 22. A boy with mass m is standing on the edge of the disc with moment of inertia I and radius r. The initial angular velocity omega. Boy jumps off the disc with a tangential speed v with respect to the ground. The new angular velocity of the disc. So this is the disc with the moment of inertia is given as I disc, is given as I, and the boy is standing at the edge of the disc at a distance r. Mass of the boy is m. Okay. Now it suddenly jumps. Before jumping of the boy from the disc, the total angular momentum of the disc by system is equal to total angular momentum of the disc by system just after jumping by a boy in tangential direction. So net force x, net torque x on the system is 0. To do that, angular momentum is conserved. So initial angular momentum and final angular momentum of the system is constant. So angular momentum before jumping of the boy. Before jumping of the boy is angular momentum LF, Li is equal to angular momentum after jumping of the boy. Before jumping, angular momentum is moment of inertia of the disc plus moment of inertia of the boy into angular velocity omega. Okay, what is the angular velocity here? It is given as omega is given, right, equal to after jumping of the boy, moment of inertia of the disc, moment of inertia of the disc into angular velocity of the disc plus here angular momentum of the boy. Angular momentum of the boy. Boy moves tangentially with velocity v with respect to axis of rotation, m into v into r. Okay, this is the angular momentum of the boy. This is for disc. So from this here, moment of inertia of the disc is I, moment of inertia of the boy is m r square into omega minus of mvr is equal to moment of inertia of the disc is I into omega dash. So from this we want omega dash is equal to I plus m r square into omega minus mvr by I is the answer. So it is the angular velocity of the disc just after when boy jumps in tangential direction with velocity v. So omega dash equal to I plus mr square into omega minus mvr by I is the answer. See the last sentence, last option, I plus mr square into omega minus mvr by I is the answer for question number 22. So net torque acts on the system is 0 because the jumping of the boy and the torque applied by boy on the disc is an internal torque. So only external torque will change. External torque will create the change in angular momentum. Here the jumping of boy on the rotating disc creates an internal torque. Only internal torque never changes the angular momentum of the system. So due to that, I consider net torque acts on the system is net external torque acts on the system is 0. So therefore net external torque acts on the system is 0. So therefore angular momentum of the boy disc system is conserved. So before jumping and after jumping, angular momentum of the system is constant. That is the central point in this problem. Okay, right. So answer is D. Question number 23. A small particle of mass m and its retaining cord are spinning with angular velocity omega on the horizontal surface of a smooth disc. A force F is slightly relaxed and r increases and omega changes. Determine the rate of change of angular velocity with respect to r. So when the small particle of mass m is rotating with the help of the cord here on circular path of radius r. This is r. Here this is the force held. By rotating this one, force is held. If force is released slowly, what happens to this radius of rotation? Gradually increases. So when particle is constantly moves on circular path of radius r by holding this one with force F. Suppose if this force is slowly released, then this particle moves on increasing path of increasing radius like this. So as F is released slowly, then radius of the path of the particle increases. Radius of the path of the particle increases. In this case here, the external torque acts on the system is 0. External torque acts on the rotating system of the particle with respect to center of rotation is 0 external torques. Therefore, angular momentum of this system is constant. What is the angular momentum of this particle under rotation at an instant of particular force at radius r is given as m r square omega. M r square omega is the equation for angular momentum of the particle under rotation. Now, this is L. So, by taking the differentiation of this one with respect to r, dl, what we want to see the question here, the rate of change of omega with respect to r, rate of change of omega with respect to r. So, d by dr of m r square into omega equal to dl by dr, but dl by dr is constant, that equal to 0. So, m into for r square it is 2r into omega plus m into r square into for omega d omega by dr equal to 0. So, m gets cancelled, we get r gets cancelled. So, we get d omega by dr into r is equal to minus 2 omega by r, okay, minus 2 omega only. So, from this d omega by dr is equal to minus 2 omega by r. It is the rate of change of angular velocity with respect to the radius of the rotation of the particle. D omega by dr equal to minus 2 omega by r. What we want to see, the determine the rate of change of omega with respect to r. So, we have to find d omega by dr, that we have to calculate. So, what is the basic process in the calculation of d omega by dr? Simply here, as force is released on the particle under rotation and on horizontal platform by means of this force, if F is released slowly, then due to that radius of rotation of this particle gradually increases. So, we consider the external torque acts on the system is 0. So, due to that angular momentum of this rotating particle is, suppose a constant, it is L is constant in the absence of external torque. Then what is the basic equation for angular momentum of this system of the particle under rotation with angular velocity omega in the path of radius small r? It is m r square omega is constant, that equal to L. Then dl by dr equal to d by dr of m r square omega. After differentiating this equation with respect to r, we get d omega by dr value as minus 2 omega by r is the answer for this question. Question number 24. Consider the combination of two discs. Then what will be the velocity of the falling disc center as a function of h? Both discs are identical and the string does not slip over relative to the disc. So, when two discs are like this, kept like this, so this is pivoted, this is only connected to a string of number of wounds. When it is released, then disc moves down. At the same time, this disc rolls about this pivot. So, when initially these two discs are kept at same point, when it is allowed to free fall like this, then first disc rolls down like this, rolls and moves down, and second disc only it rolls only. So, on this basis here it rolls like this, it rolls and moves down. It only rolls, it only rotates, first one only rotates, second one rotates and moves down. So, here when it falls down through a displacement h, all the loss of potential energy of this disc, all the loss of potential energy of the first disc, second disc is equal to gain of kinetic energy of the both disc 1 and 2. So, whatever the loss of potential energy of the second disc during its fall to a displacement h is equal to the gain of kinetic energy of these two disc system. So, what is the loss of potential energy of the one disc? It is mgh. Gain of kinetic energy of the disc under rotation only half I omega square, plus gain of kinetic energy of the disc under rolls down and moves down, that is, it is having both rotational kinetic energy and translational kinetic energy, half m v square. So, in this case half into here mk square mr square by 2 into omega square plus half into mr square by 2 into omega square plus half m into v square. See in what terms we want? In terms of h and g we want. So, in terms of h and g, in place of here r omega we write 1 by 4 into m into r square omega square is v square plus 1 by 4 into m into r square v square plus half m v square. So, half m v square plus half m v square, that is v square, m into v square equal to mgh. So, from this v equal to root of gh. So, when disk falls through a displacement h, then the velocity of the second disk, what is the velocity of the second disk at that time? So, find the velocity of the second disk. So, when it falls through a displacement h, what will be the velocity of the second disk? That we are going to calculate. Velocity of the second disk is equal to root of gh. What I considered, the loss of potential energy of the second disk is equal to gain of kinetic energy by both disks, system for 1 and 2. So, loss of potential energy is only with respect to this level. Loss of potential energy of the first disk is only mgh, and gain of kinetic energy for disk under rotation is half I omega square, and gain of kinetic energy for disk under falling, it has both translational and rotational motion. For translational kinetic energy half mv square and rotational kinetic energy half I omega square. So, I is replaced for disk mr square by 2 in all cases, and r omega is replaced by v. That is the linear velocity of center of mass of the falling disk. Because see the question here both disk and the string does not slip relative to the disk. String does not slip relative to the disk means disk falls down with pure rolling indirectly on the support of the string here. So, for pure rolling, V value is replaced by R omega. For pure rolling, V value is replaced by R omega for pure rolling. That is given indirectly. So, this disk falls down without any slip with respect to the string passed over the disk. So, due to that, here we considered velocity of center of mass after falling through a distance h is given as R omega. So, at that time initially it is adjusted. At any position it will be R omega, but in this case here by applying V equal to R omega in all these equations, we get this form. After calculation we get mgh equal to mv square. So, V equal to root of gh. So, when this disk falls through a displacement h vertically from its initial position, then velocity of the center of mass at that time it will be v. So, it is the velocity of center of mass. Okay, right. Question number 25. In a given figure, solid cylinder A is initially rolling without slipping on the horizontal surface of the wedge. All surfaces are smooth and B has no initial velocity. Okay, and B has no initial velocity. All surfaces are smooth. Then maximum height attained by the cylinder is. So, in this case here, so it is slipping. See here, all surfaces are smooth here, and B has no initial velocity here. It is B, but the mass of this one is to be given as m. Mass of this one is also to be given as m. So, here mass of the here it is wedge is also to be given as m. Then only we consider So, in this case when it rises to certain height, what we want here, the maximum height attained by this one. So, with what energy it begins to roll from bottom to inclined plane, it moves on plane surface initially, then it rises up. So, with what energy it rolls initially, half mv square plus half I omega square is the energy of A. All this energy converts into here potential energy along with rotational kinetic energy along with linear kinetic energy. So, according to law of conservation of energy here, with what is the energy of A? Energy of A equal to half m v square plus half I omega square. when it reaches to position B, when it reaches to position B at certain height here, then, so the final energy, so total energy at B for this one, it is having rotation energy because all surfaces are smooth, just it slips and moves, just it slips and moves. So at that time its equation is half m, here it is v dash square plus half m v dash square plus here it is half I omega square, half I omega square plus mgh. So what is v dash here? Because this surface is also smooth, as this one rolls and moves up, at the same time this plank, this wedge moves towards left side with velocity v dash. So as it rolls up and moves up to certain height h, its kinetic energy is half mv square plus half I omega square at point A. When it reaches B, this is the maximum height reached by this one. When it reaches B, what is the energy of this one? At that point it is also on the plank, so its kinetic energy is half m v dash square, and for Planck's kinetic energy is half m v dash square, plus it is having continuously, it is having rotation at this point half I omega square. At the same time it rises to a height h, mgh is the potential energy. So it is the total energy at B. So total energy at A equal to only half mv square plus half I omega square. So according to law of conservation of energy that equal to half mv square plus half I omega square is equal to half m into v dash whole square plus half m into v dash whole square plus half I omega square plus mgh. So in this case half I omega square gets cancelled. What is v dash? So that is m into v is equal to m plus m into v dash according to law of conservation of linear momentum. So v dash is equal to v by 2. Substitute, so half mv square is equal to half m into, in place of v dash, v by 2 whole square plus half m into v dash is v by 2 whole square plus m into g into h. So do the calculation. After calculation, h value is root of v square by 4g. So after calculation you get h value as v square by 4g is the answer for this question. So when sphere rolls, sphere or disc or solid cylinder, here when it rolls from A to B, but here all surfaces are smooth according to given data. See here, then this plank moves towards backward direction because mass of the wedge or plank is to be given in the data as m. So this moves towards left side with v dash. At the same time when plank moves back, at the same time it rolls up and again it comes to certain height, maximum height reached by this ball or cylinder or sphere is suppose h. Then total energy at point A for cylinder converts into total energy for this cylinder during movement, and for total energy for this plank during backward movement, plus here all some part of this energy will be converted into potential energy when rising to certain height from its initial reference level. So this is the final energy of this cylinder or disc or sphere, whatever it may be. So this mass is given directly. So half m v dash square plus half m v dash square plus half I omega square, because it slips and continue to roll at this point. It doesn't come to rest because it is smooth here. It slips and at this point it continue to roll. So initially it is under rolling position with angular velocity omega. Meanwhile in the path, in the middle path here doesn't roll. It slips and it reaches to edge and rolls continuously. Do that I considered here total kinetic energy in the form of rotational kinetic energy as half I omega square plus mgh. So by equating these two total energies at position A and position B, then we get h value is v square by 4g. So what is the maximum height raised by this cylinder during slipping and rolling of the cylinder according to given conditions. This is another important model question. Okay, right. Next question. Question number 26. The given figure shows two doors A and B. Same force is applied to them, which is always perpendicular to the edge. If A takes 3 seconds to rotate certain angle theta, then what time will be taken by B to rotate same angle? So here this is a door. For this door here, force is applied at the edge. Force is applied at the edge. Then what is the torque applied by the force here about this hinge? About an axis passing through hinge here, torque applied is tau equal to F into L. Due to this torque, it is I alpha is equal to F into L. I is for this rod here, it is, I consider this as rod according to given this shape. Here it is ml square by 3 into alpha equal to F into L for first case. In a similar way for second case here, the force is applied at this point. This is the axis of rotation hinge. This is force. This is L by 2. So due to that it rotates. In this case, torque by this force applied on the door at one edge is F into L by 2 is equal to I alpha. So I is, so here door rotates about an axis passing through middle. So it is ml square by 12 into alpha 2 is equal to F into L by 2, equation 2. By dividing 1 with 2, we get here it is m L square by 3 into alpha 1 equal to m L square by 12 into alpha 2. So from this alpha 1 by alpha 2 equal to 3 by 12. Alpha 1 by alpha 2 equal to 3 by 12, that equal to 1 by 4. But what is the, what we want here, due to the application of this force, what is the angle turned by the door here? Angle turned by the door equal to angular displacement turned by the door, that equal to half at square, half alpha into t1 square, alpha t1 square. Theta 2 is equal to half alpha 2 into t2 square. So we want theta 1 by theta 2. Alpha 1 by alpha 2 is 1 by 4 into t1 square by t2, t1 by square by t2 square. But what are the values are given? T1, T2s. So T1 value is given as 3 seconds. We have to calculate T2 value. So T1 value, theta 1 equal to both angles are same. B also to rotate to same angle. So theta is also same. 1. So T1 square by T2 square is equal to 4. So T2 is equal to T1 square by 4. So from this here, T1 square by T2 square equal to 1 by 4, that is T1 is 3 square by T2 square equal to 1 by 4. Okay. So T2 square equal to 4 into T square, that is 6 seconds. 4 into 3 square, that is root is 2 into 3, 6 seconds. Okay. Answer is here, it is 1 by 2, 3 by 12, 1 by 4. So alpha 1 by alpha 2 is equal to, here it is alpha 1 by alpha 2 is 1 by 4 equal to theta 1 by theta 2. So T1 square by T2 square equal to 4 it is. So T2 square is equal to T1 square by 4, T1 square by 4, T1 square is 3 square by 4, it is 3 by 2, yes. 3 by 2, after calculation we get that answer as 2 seconds. 3 gets cancelled. One by 4 into T1 square by T2 square equal to theta is same. So what is alpha value by alpha 1 by alpha 2 here? So ml square by 3 into alpha 1 equal to, here FL is there, 1 2 we forgotten. So FL is there. So therefore it is FL. So also FL by this one. So this 2 gets cancelled. So this 2 also gets cancelled. 1 by 2 it is. Okay. 1 by 2. So from this we get T1 square by T2 square, that is 3 square by T2 square equal to, here it is FL, ml square by 3, alpha 1 by alpha 2, ml square by 3 into, that value is FL by F1, it is 2 is there, it is 2, it will come. So 6 times. So 6 times 2 times here. Alpha 1 by alpha 2 equal to 2 times here it is. So from this you get t equal to 2 seconds. 3 gets cancelled, t equal to 2 seconds. Okay. So by dividing equation 1 with equation 2, here it is equation 2, here this is equation 2. So there FL is there, here FL by 2 is there. So therefore we get alpha 1 by alpha 2 value. You substitute alpha 1 by alpha 2 value in this form, but theta 1 by theta 2 value is given. So therefore it is 1 by 4 into 2 is there. So it is 2 times. So from this 2 times is there. So T1 value is given as 3. Okay, 3. So 3 by 2 is there. You get 3 by 2 you get. So 3 by 2 into 2 value. So from this 3 gets cancelled, we get 2 seconds. So for this one, F into L is equal to half into ml square by 3, ml square by 3 into alpha 1. For second case, F into L by 2 equal to, here it is ml square by 12 into alpha 2. So that is 2 by 1 is equal to, it is 12 by 3 into alpha 1 by alpha 2. So alpha 1 by alpha 2 is equal to, so it is 6 by 12, that equal to 1 by 2. 6 by 12, 1 by 2, alpha 1 by alpha 2. So but theta we want, theta 1 by theta 2 is equal to half alpha 1 into T1 square by half alpha 2 into T2 square. But this value is given as same. So alpha 1 T1 square is equal to alpha 2 T2 square. So alpha 1 by alpha 2 is given as 1 by 2 is equal to T2 square by T1 square. So from this here it is 1 by 2 is equal to T2 square by T1 square value is given as, it is 3 square. So from this T2 square is equal to 3 square by 2, 9 by 2, 4.5. So T2 square is 4.5 approximately. So from this T2 is approximately 2 seconds. It is corrected to 2 seconds. Actually T2 value is 4.5, T2 value is 2 seconds. So this is the calculation. There 2 is missing in the previous calculation. Next, question number 27. A solid sphere and solid cylinder of same mass are rolled down on two inclined planes of heights h1 and h2 respectively. If the linear velocity at the bottom for both is same, then the ratio is. So when these two are allowed to slide down over the inclined plane, then what we want here, velocity of the body which reaches the bottom of the inclined plane is root of 2gh by 1 plus k square by r square. So v1 by v2 is equal to root of for first case it is 1 by 1 plus, it is solid sphere 2 by 5 into 1 by 1 plus second one solid cylinder 1 by 2, that equal to root of, the answer for this question is root of 14 is to 15. Root of 14 is to 15 is the equation here if the linear velocity of the bottom is same. Okay, it is 3 by 2, it is 7 by 3 by 2, 7, yes. So this is the answer for question number 27, 14 is to 15. So out of all these questions here, see here, see the answer here, 7 by 5, here 3 by 2. So 3 into 14 it is. So v1 by v2, if the variables at the bottom of this one is a solid sphere, I have taken reverse it is, okay. It is v1 by v2. So we get root of 15 by 14. So v1 by v2 equal to root of 14 by 50. So answer is for 27, answer is C, direct question it is. The velocity of the body which rolls down from top to bottom of the inclined plane is root of 2gh by 1 plus k square by r square. So this is the explanation for question number 27, direct formula. You can note for solid sphere as 1 plus k square by r square as 2 by 5, for solid cylinder as 1 plus 1 by 2 is the k 1 plus k square by r square value. By taking the ratio of their velocities, then you get root of 14 by 15, but root is not there here. So, root of 14 is to root of 15 is the answer. So, in this module, I explained problems relates to rotatory motion and also work power energy. Okay, out of these 27 standard model questions, 20 questions are most important for JEE mains and JEE advanced level oriented concepts also. Okay, so be thorough regarding all these models, right? So next module we will meet in next module. Okay, thanks to all.